4.2. The development of atomic models. Question: why are there different atomic models? How did we learn that atoms could be divided? How were different subatomic particles discovered? Terms: electron, nucleus, proton, atomic number, neutron. What are atoms made of? 4.2. The development of atomic models. The invention of the electrochemical battery by Alessandro Volta in 1800, about the same time as Dalton's discovery, allowed scientists to study how matter behaves in the presence of an electric current. They found that a gas sealed under very low pressure in a glass tube can carry an electrical current between two electrodes. The glass tube was called a gas discharge tube. Scientists noticed another strange phenomenon. When most of the gas molecules were removed by a vacuum pump, the current decreased. But when even more gas was removed, the current gradually began to increase, and the tube glowed with an eerie green light. Later, scientists determined that the color of the light depended on what gas was in the tube. Removing all the gas molecules caused the glow to disappear, but current continued to flow. Obviously, something other than the gas carried the current. In a series of experiments during the late 1800s, physicists observed that current through the discharge tube came from the negative electrode, called the cathode. Emissions from the cathode were called cathode rays. Thomson's model. Discovery of the electron. English physicist J.J. Thomson finally explained cathode rays. He noted that cathode rays travel in straight lines, unaffected by gravity. That phenomenon could be explained only if the cathode rays were waves, similar to light waves or particles moving at incredibly fast speeds. He also observed that a magnet could deflect cathode rays. Thus, the rays could possibly be tiny charged particles. When Thomson passed a cathode ray between two electrically charged plates, the ray bent toward the positively charged plate. Accordingly, Thomson concluded that the cathode ray particles were negatively charged. A cathode ray tube with a magnet deflecting rays. Another scientist, George Johnstone Stoney, named these particles electrons, E-, in 1894. The E in the electron symbol indicates the fundamental charge, which was determined to be 1.602 times 10 to the negative 19th coulombs. In 1897, Thomson determined the charge-to-mass ratio, E/m, of the particle. He found that this ratio was surprisingly large. Compared with the charge, the mass of the electron was almost nothing. It was later determined to be 9.109 times 10 to the negative 31st kilograms. He concluded that he was working with a particle fundamentally different from atoms and molecules, the ordinary particles of matter. Thomson concluded that every atom contained smaller, negatively charged particles. Thomson discovered that all metals emit identical particles, electrons: silver, gold, iron, copper. Thomson further proved that the same type of particle was emitted from atoms of every element tested. Regardless of the gas in the tube or the type of cathode material, he obtained the same results. Gold, silver, iron, and copper all gave off the same particles. Dalton's atomic model with its indivisible atoms could not explain how electrically charged particles could exist in an atom, why the atom was neutral, and how negative charges could leave an atom. A new, more workable model was needed to account for Thomson's observations. In his model, negatively charged electrons are embedded in a positively charged substance that electrically surrounds them. The charge on the positive material balances out the negative charges on the electrons so that the atom was neutral. Under certain conditions, electrons could be removed from the atom. The proposed model looked something like an English plum pudding. The electrons resembled negatively charged plums in a positively charged pudding. Thus, Thomson's model is known as the plum pudding model of the atom. An analogy that may be a bit more familiar with is a chocolate chip cookie dough. The chocolate chips represent the electrons, just as they did in Thomson's plum pudding. Thomson's work earned him knighthood, as well as a Nobel Prize in Physics in 1906. Thomson's atomic model illustrates a fundamental aspect of the work of science. Whenever scientific models prove insufficient to explain new observations, they must be modified or else replaced by more workable models. As you'll see in the next section, Thomson's model needed such modification almost immediately. Rutherford's model, discovery of the nucleus. Wilhelm Röntgen's discovery of X-rays in 1895 triggered further experiments that led to the discovery of nuclear radiation. In the 20 years before World War I, the brightest minds in the scientific world pioneered the fascinating field of radioactive particles. One of these brilliant scientists was Ernest Rutherford, a native of New Zealand teaching at Cambridge University in England. His experiments with alpha particles, a form of radiation, led to new insights about the inner parts of the atom. Rutherford discovered that alpha particles are positively charged ions with a mass equal to that of about 7,300 electrons. These particles are emitted at very high speeds from some radioactive elements. Their large mass and high speed give alpha particles a great amount of energy. They are also strongly charged, having a +2 electrical charge. If an alpha particle strikes a screen coated with zinc sulfide, its energy is converted into a brief flash of light that allows it to be observed. In 1908, under his direction, one of Rutherford's assistants, Hans Geiger, and a student, Ernest Marsden, designed a series of experiments in which a beam of alpha particles was aimed at a sheet of thin gold foil that was in turn surrounded by a curved zinc sulfide screen. As the particles struck the foil, most of them went straight through, illuminating the screen in a direct line with the alpha particle source. A few, as expected, were slightly deflected and were detected by the flashes of light on the zinc sulfide screen at slight angles from the source. Unexpectedly, about 1 in 20,000 particles was deflected at a large angle or even ricocheted back toward the source. Rutherford was astonished. He compared the deflected alpha particles to a cannon shell bouncing off tissue paper. Thomson's model could not explain these observations. Already, it was time for a new model. Thomson's atomic model, showing alpha rays crossing straight through atom. Rutherford's atomic model, showing alpha rays reflecting off nucleus. Rutherford reasoned that atoms must be mostly empty space, otherwise most of the alpha particles should have been deflected. Because such a small percentage of the alpha particles were greatly deflected, there must be little likelihood that an alpha particle would collide with a central, dense region of an atom. Rutherford reasoned that this region, the nucleus, as he called it, must be very small. Subsequent calculations indicated that the diameter of a nucleus was only 1/10,000th the size of an entire atom. Rutherford's model is sometimes known as the nuclear model of the atom. Rutherford's model of the atom had a tiny, positively charged, massive nucleus surrounded by electrons. At first, Rutherford did not investigate the charge of the nucleus. Further experimentation, however, determined that the nucleus had to be positive. A decade after discovering the nucleus, Rutherford identified the positive particles in the nucleus, which he called protons, P plus or P. A proton has an electrical charge of +1 electron, exactly opposite the electron's charge of -1 electron. The mass of a proton is approximately 1,836 times that of an electron, or 1.673 times 10 to the -27th kilograms. Shortly after the discovery of the proton, scientists recognized a relationship between the number of protons in the nucleus of atoms and their chemical and physical properties. The number of protons in the nucleus is called an atom's atomic number. Completing Rutherford's model. Discovery of the neutron. Rutherford and others realized that atoms have much more mass than the sum of the masses of protons and electrons. Rutherford suggested that neutral particles supplied the missing mass without changing an atom's charge. He thought that the particle might consist of a closely joined proton and an electron. Because this hypothetical particle did in fact turn out to be electrically neutral, it eluded detection for many years. In 1932, James Chadwick observed neutral particles radiating from a sample of metal bombarded by alpha particles. Appropriately enough, these particles were named neutrons, N0 or N. A neutron has a mass of 1.675 times 10 to the negative 27th kilograms, 1,839 times the mass of an electron, just slightly greater than the mass of a proton. Neutrons and protons make up the nucleus and contain almost all of the mass of an atom. Rutherford's carbon atom. Protons and electrons, no neutrons. Chadwick's carbon atom. Protons, electrons, and neutrons.